The examples in this video go with lesson 11.3, inference on the slope of the regression line. Example 1, for each of the following residual plots, determine whether the assumptions of the linear model are satisfied. If they are not, specify which assumptions are violated. All right, let's look at plot A. And I can see that the points are kind of scattered and we're kind of moving down, and then we get to this point and then we're still scattered, but we're kind of moving up. So we can kind of imagine a little bit of a pattern going in this direction. And so since we're not allowed to have an obvious pattern, this one does not follow the assumptions for a linear model. Okay, this one has an obvious pattern. All right, let's look at plot B. For plot B, we've got the dots kind of hugging pretty close to the line right here, still hugging pretty close, and now they're starting to get a little further apart, and a little further apart, and a little further apart. And so we don't have the same spread here. And so this plot does not follow the assumptions for a linear model because the distance between the dots is not the same. And we would say that their vertical spread is not the same. All right, so B is no good. Now we'll look at C. This looks like a scatter plot right here. I can't really tell that a straight line would fall in here. I can't really see any kind of a curve pattern going on in here. The spread looks pretty even all the way across. I mean, we got a little bit of a deviation because these are a little bit closer together than these are out here, but then it kind of spreads back out again. So that's going to be looking okay. And I don't really see any outliers here. So part C is okay. This one is going to satisfy those assumptions. All right, let's look at plot D. We've got a cluster of dots down here, and they're kind of, keeping close to the line right in here, and then we've got a few of them coming off down here. So we don't really have a pattern going on here, so that would be okay. And the vertical spread kind of has been violated here because mainly these 3 points right here seem to be outliers. And when we have outliers, that means that some of our assumptions, or one of our assumptions, has been violated. So for plot D, we have outliers present. And this one would not satisfy those assumptions. Example 2, a certain data set contains 27 points. The least squares regression line is computed with the following results. B1, the slope, is 5.78. The standard error of the residuals, that's S sub E, is 1.35. And the sum of the squares of the x's is 3.4. We're going to construct a 95% confidence interval for B1. Okay. Let's back up a couple of slides. When we construct a confidence interval in here, we can start down here at number 4 where we have to find the standard error of B1. We need to find the standard error of the slope, and if we back up one more slide, we see the formula to find the standard error for the slope is right here. Now, conveniently, this number is given to us, and this number is given to us as well. This is the standard error of the residuals, and this is the sum of the squares of x. Okay, so let's go back here. All right. The S sub B, this is the standard error for our slope, is going to be the standard error for the residuals divided by the sum of the squares of x. All right, and let's put this in the calculator and see what we get. And this is giving me, oh, we got to square root that, don't we? Yes, we do. We got to square root that. Okay, hang on. I forgot to square root that. All right, let's try this again. We got 1.35 divided by the square root of 3.4. All right, and that's going to give us 0.7321. .7321. Okay, the next thing we want to do to get our confidence interval, we've done this one, and these were all done for us. We need to find the critical value, table A3. We want n minus 2 degrees of freedom. Okay, so our degrees of freedom, n is equal to 27, so we're going to have 27 minus 2, or 25 degrees of freedom. And we're going to go over to table A3. We're going to be on line 25 and the 95% column. And that is going to give us our critical value, T sub alpha over 2. All right, so our critical value, let's bring up table A3. And that's going to be right here. Okay, we're going to be on line 25. Well, let's go to the column first. The 95% column, that's this one right here. So this is 1, 2, 3, 4, 5 over. And we need to go up to line 25. That's going to put us right here. So our critical value, 2.060. Okay, next thing we need to do. We've got our critical value. We're supposed to multiply it by the standard error. This is going to give us our margin of error. Okay, so we need the margin of error. This is the critical value times the standard error for the slope. And let's see, this is going to give us 1.5082. All right, now we have our margin of error. Next, we're supposed to use the point estimate, which is the slope itself. And then we're going to add the margin of error to it and subtract the margin of error from it. All right, so our point estimate is the slope itself, 5.78. All right, let's go get our confidence interval. The confidence interval is going to be our point estimate minus the margin of error and our point estimate plus the margin of error. All right, let's put those in the calculator and see what we get. All right, and the calculator gives me these results when I subtract the margin of error from the point estimate, 4.2718. But since my point estimate was rounded to 2 decimal places, I'm going to round that to 4.27. And then the point estimate plus the margin of error gives me 7.2882. And if I round that to 2 decimal places, this is going to be 7.29. And so here is my 95% confidence interval. We are 95% confident that the slope will fall between 4.27 and 7.29. Example 3. Following is a TI-84 Plus display showing a 95% confidence interval for B1, the slope. Part A. What is the slope of the least squares regression line? Well, that is conveniently given to us right here as the slope, our b. And if we round that off to 4 decimal places, we can call this 0.1972. Part B, how many degrees of freedom are there? Well, again, conveniently given to me right here. There are 10 degrees of freedom. C, this one's not quite as obvious. How many points are in the data set? Well, remember the degrees of freedom is n minus 2. So if I have 10 degrees of freedom, then 10 plus 2, or 12 points, must be in my data set. All right, and then D, the 95% confidence interval for the slope, again, conveniently given to us right up here inside the parentheses as 0.17354 to 0.2208. Example 4. For a given data set containing 18 points, the assumptions of the linear model are satisfied. The following values are computed. The slope, b sub 1, is 5.58, and the standard error for the slope, s sub b, is 4.42. Perform a test of the hypotheses. H0, the null hypothesis, is that the slope is equal to 0, versus the alternate hypothesis, H1, that the slope is not equal to 0. We're going to use an alpha equals 0.05 level of significance, and the question we need to answer, can you conclude that the explanatory variable is useful in predicting the outcome of the variable? Okay, so what we're looking for here is if we're going to reject the null hypothesis that the slope is 0, then we are concluding that there is a linear relationship, therefore the explanatory variable is going to be useful in predicting an outcome variable. However, if we don't reject the null hypothesis, then there is a possibility that the slope could actually be 0, and in that case, the explanatory variable would not be useful in predicting the outcome variable. All right, so that is what we're going to test. All right, let's back up a few and see how we're going to do this. All right, the least squares regression line is done. The null and the alternate hypotheses are done. And this one in particular, we're doing a two-tailed test. We've got our significance level. The standard error has been done for us. So we're going to start here at step 5, computing the test statistic, which is going to be the slope divided by the standard error of the slope. And then we're going to get the degrees of freedom as n minus 2. Okay, our test statistic is going to be our slope, 5.58, divided by the standard error for the slope, 4.42. All right, let's put that in our calculator. And this is going to give me 1.2624. The degrees of freedom, well, our data set has 18 points in it. So 18 minus 2 is going to give us 16 for our degrees of freedom. Okay. All right, we've done step 5. Let's move on. We're over here. I'm going to do the critical value on this instead of doing the p-value. I don't like doing the p-value because when we use table A3, most of the time I'm going to end up getting some sort of an interval for the p-value, and I would rather do it by critical value because then we can get our exact information there. Okay, all right, so the critical value, we're going to have to use our alpha level and our degrees of freedom for table A3. Now, keep in mind, we're doing a two-tailed test right here. So our alpha level is 0.05, but since we're doing a two-tailed test, we want half of that to be back here and the other half to be over here. That means this area should be 0.025, and this one should also be 0.025. I just put 0.25 on that, didn't I? I shouldn't have done that. All right, let's correct that. Okay, so we are looking for this number right here and this number right here to compare my test statistic to. All right, we're going to be on line 16 and column 0.025. So let's bring up table A3. All right, and here it is. Column 0.025 right here in the middle. 1, 2, 3, 4. This is column 5. We got to go all the way down to 16, line 16. That brings us right here to 2.120. This is going to be our critical value. Okay, let's put these on our picture. We're going to have 2.120 at this end, and by the magic of symmetry, this one's going to be negative 2.120. All right, now let's compare our critical value, 1.2624. Does it lie in the shaded area to the right of 2.120 or in the shaded area to the left of negative 2.120? And the answer is no, it actually lies to the left back here of positive 2.120. This is where our 1.2624 belongs. Okay, so since our test statistic falls in the unshaded area, we will not reject the null hypothesis. All right, so do not reject the null hypothesis. And remember, we said if we're not going to reject the null hypothesis, that it is possible that the slope is equal to 0. And then we said that if the slope is 0, that means that our explanatory variable would not be useful in predicting our outcome variable. All right, and here's our conclusion right here. We say, therefore, the explanatory variable is not useful in predicting the outcome variable. Example 5, for a given data set containing 26 points, the assumptions of the linear model are satisfied. The following values are computed. The slope, b sub 1, is equal to 46.8, and the standard error for the slope, s sub b, is 15.2. Perform a test of the hypotheses. The null hypothesis, the slope is 0, versus the alternate hypothesis, the slope is greater than 0. Use the alpha equals 0.01 level of significance. Can you conclude that the explanatory variable is useful in predicting the outcome variable? Okay, so back to the steps we were doing before. All right, so for our hypotheses, or testing our hypotheses here, the least squares regression line is done. They've given us our information. The hypotheses have been stated, and this time we are doing a right-tailed test. Okay. The significance level has been given to us. The standard error for the slope has also been given to us. So we're going to start here with step 5. We're going to find our test statistic and the degrees of freedom. Okay. The test statistic is our slope, 46.8, divided by the standard error, 15.2. And this is giving me 3.0789. The degrees of freedom, let's see, there are 26 points, so this is going to be 26 minus 2, or 24 points. All right, and that means we have completed step 5. We want to compute the p-value, or we want to do the critical value. So this time I am going to do the p-value for the test statistic, okay? And that's going to mean that we need to be on line 24. And, well, I'm not actually going to use table A3. What am I saying? I'm going to use the ALEKS calculator this time so I can get an exact p-value. Because if we wanted to use table A3, I would want to be on line 24, and then I would be looking for this number. And like I said, we would be getting an interval for that. So let's use the ALEKS calculator to calculate an exact p-value for this particular test. All right, I'll bring up the ALEKS calculator. And we are doing a t-test, right? The test statistic we had, 3.0789. And the degrees of freedom we said are 24. All right, and that gives me a value of 0.0026. I'm going to round that up to 6. So 0.0026 is going to be our p-value. Okay, now let's take a look at the picture so we can decide whether we want to reject the null hypothesis or not reject it. We are testing our alpha value right here of 0.01. All right, that means from here on out, the area in here is 0.01. Now, the question is, my p-value down here, I'm going to change colors, actually, I'm going to do this. All right, is this going to be less than 0.01, in which case we would be drawing our line back here and shading in this for the 0.0026, or is it more than that, in which case the critical value that went with it would be right here, and it would actually include some white area and also the shaded area. And in this case, I hope you can see that it is going to be a case of the p-value actually being back here, okay? Now, the test that we've been doing to decide whether to accept or whether to not accept is we're trying to make sure, is our p-value less than the alpha value that I'm given? And in this case, yes it is, because our p-value is 0.0026, and that is less than 0.01. So we are going to reject the null hypothesis. At the 0.01 level, because our p-value, 0.0026, is less than our alpha value of 0.01. And then our conclusion, remember, since we are going to reject the null hypothesis, we can conclude that there is a linear relationship and that our explanatory variable would be useful in predicting the outcome variable. All right, and down here I actually have our conclusion. We are going to reject the null hypothesis at the 0.01 level because 0.0026 is less than 0.01. Okay, that is, our p-value is less than the alpha value. We can conclude that a linear relationship exists and the explanatory variable would be useful in predicting the outcome variable. Example 6. The following TI-84 Plus display presents the results of a test of the null hypothesis. The slope is equal to 0. Part A. What is the alternate hypothesis? Well, conveniently, up here in the first line, the alternate hypothesis is given to me. The slope is not 0. So this is going to actually be a two-tailed test. Part B, what is the value of the test statistic? Well, remember, that's a t-value, and so that's going to be located right here. We're on line 3, and I'm just going to round that to 4 decimal places, so that's going to give me 2.9065. Part C, how many degrees of freedom are there? That's going to be right here. This is the second one from the bottom. There are, in fact, 10 degrees of freedom. Part D, what is the p-value? That one's given right here. The p equals, and again, I'm going to round this to 4 decimal places, so this is going to be 0.0157. All right, part E. Can you conclude that the explanatory variable is useful in predicting the outcome variable? In other words, are we going to reject the null hypothesis or not? Our alpha level is going to be 0.05. Now, since they gave me a p-value here, I'm going to use our p-value method. And our p-value here is 0.157, and that is in fact less than 0.05. So we will in fact reject the null hypothesis, and we would say that the explanatory variable is going to be useful in predicting the outcome variable. And I have our conclusion right here, and I did a little bit of shortening here so that I didn't have to write the whole word out there. But yes, we're going to reject the null hypothesis, and we would say the explanatory variable, EV, is useful in predicting OV, the outcome variable.